Here I have a 300 megahertz oscillator and a 100 watt radio frequency amplifier that's going to be amplifying the output of our 300 megahertz oscillator and sending it to this dipole antenna to transmit radio waves. Let's turn it on and see what effect it has on this 8 watt, 1 foot fluorescent light bulb. If I bring the fluorescent light bulb near the end of the transmitting antenna, it lights up, even though it nor I is plugged into anything. If I slide it along the length of the dipole antenna, we notice that the intensity decreases and is a minimum at the middle of the dipole antenna, and then increases in intensity again as I go towards the outer edge of the other side. It's then dim once again, once I go toward the middle, and maximum on the ends. So this is evidence that there's standing waves that are set up on our dipole antenna with a maximum in potential or antinodes at the ends and a minimum in potential or a node in the middle. We can see a similar effect if I take a simple receiving piece of copper pipe as a receiving antenna. It's about 48 centimeters long. And if I hold it in the middle and bring the fluorescent bulb toward the end, it lights up, even though it is not plugged into anything. And as I move the fluorescent bulb along the length, the amplitude is dimmest at the middle and maximum at the ends. As we saw for the transmitting antenna. Recognizing that the current is the maximum in the middle of our antenna, we're going to switch to one that has a single light bulb and use its brightness as a measure of intensity. As I move the receiving antenna closer to the transmitting antenna, the amplitude gets progressively stronger. We can also see that if I rotate the antenna relative to the orientation of the transmitting antenna, its intensity is 0 when the receiving antenna is perpendicular to the transmitting antenna, and maximum when it is parallel. We can also see that if I rotate the antenna or align the antenna along the axis of the receiving antenna, that the strength goes down. And if I rotate it so that it is perpendicular to the axis of the antenna, its intensity is 0. Lastly, if we look at the intensity of the antenna or the receiving antenna as I move in a cylinder around the transmitting antenna at a constant distance, we can see that the intensity stays constant. These help us visualize the radiation pattern off of the transmitting antenna. Here we have a different kind of antenna from the one that we saw earlier. Formerly, that long, straight conducting antenna was a dipole antenna that was sensitive to the electric field. This is a B-field antenna that is sensitive to the magnetic field. It has a loop to have currents induced within it and a light bulb that is connected across a portion of the loop, and also two parallel plates that act as a tiny capacitor, which we can tune using this ruler to adjust the spacing between them. Let's take a look at the luminosity of our detector in several different orientations. We can see that with the loop parallel to the plane of the antenna, it has a high brightness, whereas if I rotate it by 90 degrees this way, it has a minimum brightness, and if I rotate it by 90 degrees once again, it also has a smaller brightness as compared to the original orientation. This tells us that the B field is maximum in this direction, that it is parallel to the normal of the plane of the B field loop antenna.